Okay, great. So let's start. So hopefully we will finish all the organic reactions today, and then we can work on this worksheet together. Okay. So for some of the questions that we cannot finish, you can do it as homework, and then you can write your name on it right now. And right, yeah, you should be seeing the screen. Last time, let me go back to S6. Yeah, so we stop at this question, okay? And have you figured out the answer to this question? Dehydration. Yeah, so dehydration of alcohol. So how many products can you get from the dehydration of this compound? Any answer? Three. Okay. Oh, maybe you already know what the tricky thing is about this question. So first, you can remove two. There are two ways to remove water on this compound. So you can maybe draw them both out. First, it's this one here. You see an H on this carbon, and you also can find another H on this carbon in here. And when you remove them, okay, you can get water at these two positions. So you can remove these H and OH to form water at this position. You can also remove H and OH from these two carbons. So you can therefore get two compounds from it. So this is the first compound, and this is the second compound. If water is eliminated from this position and from this position. But how come there should be three answers then? That's because, do you remember stereoisomers, learning about stereoisomers? Which of these alkene can have a stereoisomer counterpart? Is it the top one or the bottom one? The bottom one. Why not the top one? What is the requirement? Let's go back a few pages back. What is the requirement for something to have cis transisomer? Let's review this. First, it has to have a cis double bond, and both carbons has to have two different groups attached to them. So let's see which of these compounds have those two requirements checked. So we find the C double bond in here. But what are the two groups attached to this carbon? They are hydrogen. Yeah, so that means it doesn't qualify. Okay, it will not have cis transisomer. So can you maybe draw it more clearly like that? So you have 1, 2, 3, 4, 5 carbon in total. The leftmost carbon, it simply cannot have cis transisomer, as it has two identical hydrogen attached to it. But what about this one? Does it qualify? Well, it does. Okay, you have C, 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 C. Now we have the double bond between the second and the third carbon. And both of these carbons in the double bond, they have two different groups attached. Do you see this? Okay, so this is why the bottom one can have cis transisomer. So this has no cis transisomer, and the following has cis transisomer, which is why there are three products in here. Okay, this one, which has no cis transisomer, this one, and it's, oh, by the way, can you name this configuration? Are we seeing the trans, or are we seeing the cis isomer right now? Trans. What does trans mean? It means the two groups, are they on the same side or opposite side of the double bond? Opposite side. So you can draw dotted line here to check the relative position of the two hydrogen. You can see that they are on two opposite sides of the C double bond. So can you also draw out the cis isomer then? Yeah, so because I want to know if you guys know how to draw the cis isomer for both of these compounds. Let me shrink it down a little bit. I'll put this on top, and then let me shrink this down a little bit. If this is the trans isomer, what does the cis isomer look like? So you have 10 seconds. Draw out the cis isomer of this compound. It will look a bit weird. Okay? So remember, trans means, this is just a reminder. Trans means, for example, this compound. This is 1,2-dichloroethene. it can exist in two forms. This is the trans form, and this is the cis form. So if this is how we draw the cis and the trans form of the same alkene compound, what about this one? How do we draw the cis form of this compound? It will look a bit weird.
Sorry.
Okay.
Well,
Yes.
the first one is trans. I thought that like two hydrogen is like in the same side.
Oh, they are on opposite sides. Yeah, let me draw it more clearly here. So you have C, C, double bond C here, and then C, C. Can you see that the two hydrogens, they are on opposite sides?
Oh.
There's a hydrogen here, hidden. There's another hydrogen here.
Oh, we
also.
don't make it like how say strict line first.
Sorry.
Do we not do it like strict line first and we fill out the
Oh,
hydrogen?
when you show this is transisomer, you have to show the double bond, and you cannot draw it as a linear chain.
Oh.
Yeah, you cannot draw it as a linear chain. So this compound actually is the same thing as this one here. Yeah, this one. So can you see that the two hydrogen, they are on opposite side? Yeah, so this is the trans form. So what I want you to do now is to draw me the cis form. The cis form. So if this is what trans form look like, and here's another example of a trans-cis pair of compound, what would the cis form of this compound look like? I want the skeletal formula. The skeletal formula. Okay? 10 seconds, all of you. Try to draw it. So, let's check the answer, okay? We have C, C double bond in here. To draw the transform, you can just swap the position of these two groups, okay? So you have C, C, and then you have H in here. And remember, by default, we don't show the hydrogen, right? So what would this look like in skeletal formula form? It will look like this. I know, bit weird, right? So take some time getting used to it. So try to draw this out. This is the trans form, okay, on the left, and this is the cis form on the right. So I'll draw it here. So you have this. Yeah, so this is the cis form. So we have a total of 3 products then. Let's number the products. The first product, the second product, and the third product. They all result from the dehydration of this compound. Okay, what is the name of this compound? I think we didn't put down the name of this compound last time, so let's do this now. And I also want all of you to name the products for me, not just the starting reactant. Can you also name the product? Let's put down the name of this starting alcohol first. What do you call this starting alcohol?
Pentanetol.
Pentanetol. Pentanetol. Remember to write everything in lowercase and mind the punctuation. Pentanetol. What about the products? We have 3 products. Can you name them all? Starting with this one.
Pen 1N.
Pen 1 in. Yes, pen 1 in. So put down pens 1 in. The bottom one. Trans. Pen 2 in. Yes, so trans pen 2 in. Actually, both of them are called pen 2 in. It's just that one is called trans, one is called cis. Okay, so cis and trans. Okay? Any question about dehydration? No. What are the 2 reagents for dehydration? We can either use concentrated sulfuric acid or aluminum oxide. Okay, aluminum oxide. So remember this. And now we will look at the setup. Okay, for when we use aluminum oxide. Okay, so this is what the setup looks like. It looks kind of like cracking, if you ask me. So you have so in here, this is the alcohol. So the starting alcohol, yeah, it is soaked in a mineral wool, and then we have in here the aluminum oxide catalyst. Just like with cracking, you must not heat the alcohol directly. Okay, for one, it is flammable, and secondly, if you heat the alcohol directly, it will vaporize. Okay, instead of being dehydrated. So therefore, we must heat the catalyst instead. So heat the catalyst instead. And can you put down why? So we must not heat the alcohol directly, just like in cracking. Because number one, the alcohol will vaporize instead of dehydrating. Okay, so instead of dehydrating, if you heat it directly. And second, alcohol is flammable. You don't want to heat something flammable directly. Okay, so these are the two reasons. It will vaporize instead of dehydrating, and it will catch fire, okay, if you heat it directly. So we heat the catalyst. And as you heat the catalyst, some of the heat will be spread back to the alcohol, causing it to, go through the catalyst, and the actual dehydration reaction happens on the catalyst. And then we can collect the product here, okay, over water. We can collect the product over water because alkene soluble or insoluble in water? Insoluble, okay? Note that you can only collect something over water when they are insoluble in water. I mean, if they are soluble in water, they will go into the water. You're not collecting it inside the measuring cylinder, right? So make sure this makes sense. And just like with cracking, do you all remember the precaution with this kind of setup? Whenever you insert a tube into water and the reaction will produce gas, should you turn off the heat before you remove the delivery tube, or do you remove the delivery tube first before you turn off the heat? It is the same precaution as in cracking. Which should we do first? Remove the tube. What will happen if I turn off the heat before taking out the tube from the water? Suck factor. Okay, there's this phenomenon called suck factor. Okay, for those of you who do physics, heat contract. Heat expand, cold contract, right? The moment you turn off the heat, it will cool down. As it cool down, it contract. As it contract, it will suck water into here. You create a vacuum here. Okay? Yeah, I will not let you do this in the lab. Don't worry, you can't experience this firsthand. So just take my word for this. Okay? Remove the tube. So this is step one. And then you turn off the heat. There is a specific order in which these things are, the setup is disassembled. So how to disassemble this setup? Okay, so how to disassemble this setup? We don't just set things up, we have to, put things back where they are. Step one is to remove the delivery tube before you think about switching off the heat. So delivery tube. And step two is to turn off the heat, or turn off the Bunsen burner. So turn off the Bunsen burner. Yeah, otherwise, so if done the other way, if you do step two first, like a phenomenon called suckback will occur. Okay, suckback of water, okay, so will occur. Because, when the test tube cools, if you do it the wrong way, the air inside the tube contracts because heat expand, cold contract. And as it contracts, it will suck water back into the tube. And because this tube is still mostly hot, when cold and hot things come together, it will crack the glass. And it will be sending debris in your direction. If you're not wearing goggles, you might be injured. Okay. So air in the tube contracts. So water will be sucked into the still hot tube. Okay, so still hot tube, cracking it. Okay, so cracking it, dangerous therefore. We don't do it this way. This is the setup, and the question that they really love to ask is which should be removed first. Remove the tube first before you turn on the heat. Okay. Now that we are done with the dehydration reaction of alcohol, do you all remember what's the other reactions of alcohol other than dehydration? Oxidation, and also substitution. We'll discuss substitution very quickly first. Okay. So you can use let me use this remaining space in here. So substitution with halide. Okay, so there are two different sources of halide, you can say. So two reagents Okay, yeah, so two reagents can be the source of halide. And one is HX, hydrogen halide. Okay, so hydrogen halide. And the other is PX3, so phosphorus trihalide. So phosphorus trihalide. And let me just check if you have done revision in the microscopic world 2 chapter. What is the name? What is the shape of the PX3 in here? So you know PX3. What does it look like? How do you draw the Lewis structure of it?
Tetra something.
Actually, so which is your final answer? There cannot be one correct shape. Is it tetrahedral or is it?
No, not tetrahedral. Three.
Trigonal.
Trigonal pyramidal. Trigonal pyramidal.
Trigonal pyramidal. Let's see why. When you draw the Lewis structure of PX3, this is what it looks like. So we have lone pairs here, and then around the phosphorus. This is PX3. And when we consider the shape, only the electron pairs around the central atom matters. We see 3 bond pairs here around P. And we see 1 lone pair also around P. So that would give a total of 4 electron pairs, right? So 4 electron pairs. Normally, if these 4 electron pairs are all visible, you will see tetrahedral, which is maybe why you said earlier, most of you said earlier that this is tetrahedral. But then you know, we cannot really see lone pair. Lone pair are invisible to our naked eyes. So therefore we can really just see something like this. You see, this is the lone pair. And these are the 3, bonds, okay? If you consider all the electron pairs, yes, this will be tetrahedral. So this will be, tetrahedral. But because we can really just see the bond pairs, meaning just these parts, what is this shape reduced to? So what does it look like to you? This looks like what you'll find in Egypt. Okay, it looks like a pyramid, right? Yeah, pyramidal. So this is why the actual shape of this molecule is trigonal or trigonal pyramidal. Okay, so this is the shape of the molecule. We can only see bond pairs. We cannot see lone pairs in a molecule. Yeah, it's similar to asking you what is the shape of CH4 and NH3. Let me draw you CH4 and NH3, and maybe you can then tell me what is the shape of these 2 molecules. So you have NH3 here. Yeah, don't worry about those fancy lines in here. This just means pointing out of the screen. This means pointing away from you into the screen, okay? It's to show perspective, 3D perspective. What is the name of the shape of these 2 molecules? This one is tetrahedral, because you really do have 4 bond pairs in here, right? You see. Remember, we can only see bond pairs. Our naked eyes cannot see lone pairs. So, and on the right, you see 3 bond pairs and 1 lone pair. So this is exactly like PH3 then, you see. The shape of this molecule is trigonal or trigonal pyramidal. Yeah, and the shape of CH4 is tetrahedral. Do you see the difference? Okay, I like to always use these molecules to draw comparison. So the shape on the left is actually tetrahedral. The shape on the right is trigonal pyramidal. So trigonal pyramidal, they are not the same. Having a bond pair swap with a lone pair makes all the difference. And this is what PX3 happen to look like, okay? And I encourage you to go to this simulation. If you you can visit this online, and there's this very useful simulation. So when you look at the model here, I can just keep adding. We have 3 bond pairs and 1 lone pair, right? So this is what you'll see. This is the shape of the molecule, trigonal pyramidal, you see. Okay, but if I replace that lone pair with a bond pair, you will see that the shape will be changed to tetrahedral. Do you get it? Yeah. Okay. Yeah. We will not be making these models, but you can picture this. Okay. In your head like that. And then we have the angle of 109.5 degrees here. So now let's take a look at the back to here. Substitution with halide. There are two reactions. Okay, let me put down PX3 is trigonopyramidal. Yeah, it is not tetrahedral. Okay, so on the next page we look at the reaction. When you react ROH with HX compared to when you react ROH with PX3, what kind of product do you expect to get? Remember we call this substitution, right? So substitution means they swap places. So we will swap them around. So we swap them around. And the OH here, it cannot swallow all the X's, okay? Which is why you only get one RX at the end. Let's look at the first equation first. You will get H2O. Because HOH means H2O. Okay, when the OH takes the place of X, this becomes OH. HOH becomes H2O. The second thing is a little bit more complicated. You will need 3 of the ROH, first of all, to completely swap out, you know, the X's. Yeah, and you will get H3PO3 in here. Okay, H3PO3. Does anyone remember learning this in, I think back in Form 4 maybe? You know, no. No. Yeah, but you may remember its brother, H3PO4. It's its phosphoric acid. This one is its brother, phosphorus acid. Okay, so can you put down the name? Phosphorus acid. Okay, not the same thing as H3PO4, phosphoric acid. Not the suffix here. Okay. Right. The reason why we need to put a 3 here is a single OH is not sufficient to substitute all 3 halogen in here. Yeah, so we don't have to put any number here because they can already swallow each other. One OH is enough to swallow an X. But one OH alone is not sufficient to swallow all 3 X's, which is why you need to put a 3 here. Okay, so understand the mole ratio, don't just memorize it. At the end, you will get a haloalkane in the end. So you have the starting compound here, and alcohol is effectively turned into a respective haloalkane. But it's up to you. It's up to you what halide to substitute. You can use HCl, and then you get RCl. If you use HBr, you get LBr. Okay, yeah, just be flexible in the exam. X can be Cl or Br or I. Okay, so Cl or Br or I, any halogen. Right, so this is what we call number 2 in the reaction. It's called substitution with halide. Really, there's nothing too special about this reaction. Okay, just remember the equation. That's all. The third and the last reaction is the most important reaction of alcohol. It's the oxidation of alcohol. Remember earlier we discussed the different classes of alcohol. How many different classes of alcohol are there?
3.
There are 3. Okay, and you should remember that I said the fate of these different types of alcohol is different depending on the class. And now we are looking at it in this an MPL-like thing. So you have primary alcohol will first be oxidized at aldehyde, okay, into aldehyde, and then to carboxylic acid. So when we go forward, we call this oxidation. So you can put down some labels first. So going forward means oxidation. Oxidation is done by oxidizing agents. So oxidizing agent, they are represented by a square bracket O. The square bracket O means oxidizing agent. And going backward, we call it reduction. Okay, so and the carboxylic acid can be reduced back to alcohol, or the aldehyde can be reduced back to primary alcohol. Okay, it really looks like like a map, menstrual map. So you have reduction by a reducing agent, bracket H. Yeah, I know on the textbook it says bracket R, but trust me, more commonly we write the reducing agent as a bracket H. So bracket O means oxidizing agent. There are two oxidizing agents that we have in the chemistry lab, but the most commonly used one is K2Cl2O7. So K2Cl2O7 acidified. And the other one is KMnO4 acidified. Okay, you may want to put down the name just once. Okay, I don't like to ask students to copy these words, but for once, put down the name. Acidified dichromate 6, or sometimes you will just not see the number 6. Okay, the 6 is to highlight the oxidation number of Cl. And then we have acidified, I forgot potassium, sorry. Okay, so there should be potassium in here, my bad. So this is potassium, and this one is also potassium, but permanganate this time. So permanganate 7. So these are the oxidation number of the elements Cl and Mn. So they are the oxidation number of Cl and the oxidation number of Mn. Okay, so these are two oxidizing agents. We have also two reducing agents to know about at this level. So we have square bracket H. These represent reducing agents. We have LiAlH4, lithium aluminum hydride, and NaBH4, sodium boron hydride. Okay, so NaBH4. And don't worry, you don't need to know the name of these two. Okay, just recognize it when you see it in question. So lithium aluminum hydride. Hydride ion are H minus ion. They are not hydrogen ion. Hydrogen ion is H plus ion. Hydride ion means H minus ion. So you can put down this means H minus ion. Unlike hydrogen ion, which is H plus ion, the one you learn in SN-H chapter. So, and then we have sodium boron hydride. And it's very easy to remember these four. Why? Because out of these four agents, there are two that are strong, two that are weak. Okay, K2Cl2O7 is the weaker one. Okay, so you can put down this is weak, and this is strong. LiAlH4 is the strong one, and NaBH4 is the weak one. And the other important thing you need to know about this agent is that LiAlH4 cannot be used in the presence of water. It will explode in water. So it can only be used with organic solvents. So put down this important note on the side. So note, LiAlH4 cannot be used with water. So what do we use to dissolve it? Right? Then we use ether, ETHER, okay, which is ethoxyethane. You don't need to know what that real chemical is, just call it ether. So it cannot be used in water because it will explode. Yeah. So it must be used in organic solvent, such as ether, dry ether. For those of you interested in knowing why it will explode, this is the equation. I said it contains H minus ion, right? When the H minus ion come into contact with water, two very dangerous things will be produced. One is H2, the other is OH minus. Even if the H2 doesn't get you, the hydroxide, the corrosive hydroxide ion will get you. So these are two very hazardous substances. What is the hazard symbol associated with hydrogen? It's an F word. Flammable, yeah, flammable, put down flammable. This is why the last thing you want to put into hydride is water. Okay, the second is hydroxide. Hydroxide is corrosive. Yeah, when you put hydride in water, you are producing these two very hazardous substances. So they can give you this equation and ask you what hazard symbols are associated with it. Just know this is flammable with a fire sign. Yeah, and this is corrosive with a test tube with liquid dripping out, and then there's a hand underneath like that. Yeah, so just recognize this symbol. No need to draw it. Okay. Now back to the pathway here. We have oxidation and reduction for primary alcohol. What about secondary alcohol? Secondary alcohol can only oxidize to ketone and they stop there. They cannot go any further than this station, you see. Then they can go back from the ketone into the secondary alcohol. So tertiary alcohol can't get anywhere, even with the strongest oxidizing agent. So they're stuck at this station forever. Okay, so they cannot get out of this position. So you have these three different classes of alcohol, which is why we need to classify alcohol before we learn what will happen to them. So primary alcohol, put down there's a two-stage oxidation. So you see it can go forward two stations. You see one station at aldehyde, another station at the carboxylic acid. By the way, put down what they are. Yeah, I'll just put this once. And later I will be referring to them as RCHO and RCO alkyne. Make sure you know what they mean. RCHO means aldehyde, RCO alkyne means ketone, and this is of course carboxylic acid. So you see the class matters a lot. Okay, it determines how far they can go and what they will become. So primary alcohol undergoes a two-stage oxidation. Secondary alcohol undergoes a one-stage oxidation. And just one more note before I overwhelm you with information. Okay. Another note that I want you to put down for the oxidizing agent is their color. When an oxidizing agent oxidizes other substance, what will happen to them? You know, if I'm an oxidizing agent, if I oxidize you, what price do I have to pay?
Lose color.
I will be reduced, right? Yeah, so put this equation that you have learned before down. When an oxidizing agent reacts with a reducing agent, what will happen to them? The oxidizing agent will be reduced, and it's like karma. Okay, when you oxidize others, you will be reduced. Okay, like you have a price to pay. Okay, so this is reduced. And when the reducing agent reduces other guy, itself is oxidized. Yeah. Let me give you an example. What if I have MnO4 minus? You should remember the color of these three things. Can you predict the products? Yeah. Can you predict the products? Mn2 plus. Yes. Okay. MnO4 minus will become Mn2 plus. So it will be reduced to Mn2 plus. So if this is reduction, what will happen to the Fe2 plus then? Oxidation. What has a higher oxidation state than plus 2 in iron? Fe3 plus. What is the color?
Brown.
Brown, yes, okay. Actually, it can also be yellow depending on the concentration. When dilute, iron 3 plus is yellow. When concentrated, iron 3 plus is brown. Just like tea, you know. Okay, yeah, when you have very concentrated tea, it's brown. Okay, so you have redox. Okay, so this is Fe3 plus. Which is why we need to know the color changes of these two oxidizing agents. When dichromate, okay, acts as the oxidizing agent, it will be reduced to chromium 3 plus. When permanganate ion acts as the oxidizing agent, it will be reduced to Mn2 plus. Okay, so can you put down Cl3 plus? This is how we know if oxidation has taken place. If oxidation has taken place, these oxidizing agents, they will change color. Yeah, you know, oxidizing agents, they don't talk. Okay, no, but the products talk. I mean, they are all colorless. Alcohol is colorless, aldehyde is colorless. How do you know if the alcohol has been oxidized to aldehyde? Is to look at the color change of the oxidizing agent, The oxidizing agent will change color. So can you all put down the colors of the oxidizing agent? You have, let me put this in here. When you have KMnO4, what is the color of KMnO4? Color of KMnO4? Purple, yes, it's purple. So this is KMnO4. The active ion is MnO4 minus. It will be turned into Mn2 plus. What's the color of Mn2 plus? It's colorless or very, very pale pink. So pale that you can assume that it's colorless. Okay, so let me use this very, very pale pink color in here. So this is M2 plus, okay? So you can say that this is purple, and this one is very pale pink or colorless. Okay, so you have this color in here, color change. And this is reduction that happens to the oxidizing agent MnO4 minus. And when you use Cl2O7 minus, what is the color of Cl2O7 minus? Orange, yes. So Cl2O7 minus. I don't know why when I look at this, I just know it's orange. Maybe it has all the letters in orange. Maybe it's all R and yeah, maybe not C. But to me, this word just look orange to me. Okay. So this is orange. Yeah, and it will be reduced to chromium. It will be reduced to chromium ion, which is green. Yes, chromium has a charge of 3+. It is a transition metal. So when you refer to it, make sure you say chromium bracket free. Chromium bracket free. So can you write down the name of these ions? This is permanganate. It is purple. It will be turned into manganese. Don't spell magnesium. I see a lot of students confusing Mn for magnesium. It is not magnesium. Magnesium is Mg. Manganese is Mn. Okay. So write manganese 2, as this is a transition metal. This one we call it dichromate. And this one we call chromium-free ion. So chromium, Roman number 3. And this is reduction. We can tell if oxidation has happened just by looking at the oxidizing agent. Okay? If they change color, oxidation must have happened. If they do not change color, if they remain purple for manganate, permanganate, or orange for dichromate, it must mean that oxidation has not happened. Let me tell you, when do you expect a color change? When do you not expect a color change? Yeah, so on the right, can you put down a very important title? We can use the color change of the oxidizing agent to determine if oxidation has happened. Okay, so if oxidation has happened, let me show you the logic. Okay, if oxidation has happened, the oxidizing agent will be reduced. And if it is reduced, a color change will be observed. Okay, so if oxidation has happened, then the oxidizing agent will be reduced. And if they are reduced, a color change will occur. Yeah, a color change in the oxidizing agent. Either MnO4 minus or Cl2O7 minus will be observed. And that's how we know that oxidation has happened. So remember, when oxidation happens, a color change will occur. Which brings us to this question. Can you tell me what will happen if I add a few drops of K2Cl2O7, this is K2Cl2O7, into primary alcohol? And what happens if I add a few drops of the same reagent, K2Cl2O7, into tertiary alcohol? What will I see after some time? You can refer back to this map. Which of these alcohol is very stubborn? It refuses to be oxidized. Tertiary. That means the oxidizing agent cannot do a thing to it. It cannot oxidize it. So let's review our deduction here. If oxidation did not happen for tertiary alcohol, the oxidizing agent will not be reduced. And if the oxidizing agent will not be reduced, meaning it doesn't go forward, the color will remain unchanged, right? Yeah. So can you all show me what the final color is like? Okay. So let me draw it 2 times, and here draw it 2 times, and then I'll shrink it. It's taking up too much space in here. So you can put down on the left. It will go from orange to green. Okay, so it will go from orange to green, indicating that oxidation has taken place. And on the right, it will stay orange. Yeah, and just like the 4 or 5 students change of the indicator, they never tell me the color change, they only tell me the final color. So I want to remind you all as well. Don't make mistakes. When they ask you for color change, I really expect 2 colors. Don't tell me the final color, okay? That's not enough, okay? So you can put that on the left. Oxidation has happened. Okay, so oxidation has happened. So this is why it turned from orange to green. And on the right, oxidation has not happened. Okay, so has not happened. Because tertiary alcohol resists oxidation. So you see what I mean? Yeah, and you can write down this equation below. I think this will make it even clearer. Cl2O7 2-, for it to become reduced to Cl3+, a concurrent oxidation reaction must happen. For example, primary alcohol into RCHO or RCOOH. What about on the right? A tertiary alcohol cannot be oxidized. It simply cannot go forward. Okay, it cannot go forward. There's no oxidation. If it cannot go forward, there will also be no reduction reaction taking place for Cl2O7 2-. The reaction is stuck here. Is that clear? Okay, you just can't go past this point because the oxidation must happen together with reduction, which is why we call that chapter redox. Redox means they must happen together. So if you have reduction, you will have oxidation. No oxidation means no reduction. Okay? Right. Now we look at another aspect. Okay, how we predict the product. How do we predict the product? Okay, and can you put back some conditions first? So you need to remember also the condition. For secondary alcohol to RCO alkyne, yeah, we use reflux. I'll explain what that means. For primary alcohol into aldehyde, we use distillation. If you want aldehyde to go into carboxylic acid, you can use reflux. And finally, we have another variation here. Is you can also go directly from primary alcohol into carboxylic acid by doing reflux. Okay? And this brings us to the difference between reflux and distillation. It is really just 2 ways of carrying out the reaction in the lab by assembling the glassware in a different ways. Okay? Have you all done distillation before? Maybe in Form 4? No. So, okay. Doesn't matter. I'll see if we can maybe arrange reflux, okay, in the lab. Okay, but I'll just see because it takes a long time reflux. It will take 4 hours. I mean, yeah, we're not staying there to look at the reaction for 4 hours, no. But yeah, I'll talk to the lab tech to see if it's possible. Okay, so we have heat. Put down what these 2 mean. You need to draw it in the exam. Heat with distillation. And on the right is heat under reflux. These are the names of 2 conditions. When you see the word state the conditions, that means they are expecting you to write either reflux or distillation. So 2 conditions, yeah, to carry out oxidation. Know how to draw it and pay attention to the detail when you draw it. For distillation, the thermometer, this is where I see most of the mistakes. The top of the thermometer must be facing the exits to the condenser. It cannot be higher or lower than the exits. It must be facing right at the exit. You see, I'm placing them at the same level. If you put it too high, will you over or underestimate the boiling point? If the thermometer is placed too high, underestimate because you are further away from the heat source. If you put the thermometer lower, closer to the heat source, you will get an overestimate of the boiling point. So therefore, put down if the thermometer is too high, if the thermometer is too low, yeah, what will happen? So this is wrong, this is wrong, this is right, okay, yeah, and then you can put down this would underestimate boiling point of the substance, and this will overestimate the boiling point of the substance, and this will give you the actual boiling point of the substance. So let's complete the rest of the diagram. We will have a round bottom plug in here with some anti-bumping granules inside. Okay, we don't want any bumping because whenever there is bumping, some of the liquid will just bump out of the round bottom plug into the condenser, which is unintended. You know, only things with the right boiling point should be able to enter the condenser. So if bumping occurs, you cannot stop that. Okay, you cannot stop the irrelevant substances from going into the condenser. So this is why anti-bumping granule is also pretty important. So anti-bumping granule. And especially with alcohol, like I said, we should never heat alcohol directly. So how do we heat something without using negative flame then? We can either use electric heater or we can use water bath. Okay, so therefore you want to surround the round bottom flask with a water bath. This is to avoid direct heating. So you can put down because alcohol is flammable. If you heat something flammable directly with negative flame, you are committing suicide. Okay, yeah. So alcohol is flammable, so therefore must not heat directly. This is what the water bath is for. Use water bath or electric heater. Anything without a negative flame will do. Okay, yeah. So use water bath or like an electric heater. Oh, I also noticed that in this is a side track. Sometimes you see the experiment using oil bath instead. Can you tell me when do we use water bath? When do you use oil bath? Is it just a matter of personal preference? What is so special about water? At what temperature does it boil? 100. So if the substance you're boiling has a boiling point above 100, don't use water bath because the water will be long boiled before the substance can even boil. You see what I'm saying? Let me give you an example. If you, let's say this substance has a boiling point of, let's say 60, well then water bath is fine because the water will not boil when this substance boils. But what happens if this substance has a boiling point of 260? Well, that means when all the water has boiled, the purple substance is still there inside the flask. Yeah, you can't invite it over to the other side. So you see what I'm saying? In that case, use oil bath because oil can have a higher temperature than 260. Okay, this is not a matter of personal preference. Okay, write this down as well. These are some very common exam type questions. So use oil bath. Yeah, so use oil bath if the boiling point, can you see the color yellow? Okay, let me zoom in closer. Use oil bath if the boiling point of the substance you are trying to distill. Yeah, you are trying to distill has boiling point greater than 100 degrees. A water bath will certainly not work here. Okay, yeah, this is very, very popular type of question. Okay, let's move on to the next part. How do we connect the condenser to water supply? Which end should water enter and which end should water exit? Yeah, and at which end should we put in the water? Do we add water from on top and let water out from below? Or do we add water from below and let it out from above? You mean you let it in from above? No, you let it in from below. You know gravity, right? When you let water in from above, it will take the shortest path possible. It will just go like this. Would it fill up the condenser completely? No. You know what the condenser is for? It's for cooling down the vapor into a liquid. You want it to be fully saturated with water. So for those of you who have maybe water cooling at your desktop, in your desktop system, you will know you need to fill it with water completely for it to work, right? So let's see what happens when we let water in the right way. You let water in and here, because gravity will settle stuff. Okay, so it will fill up this part until it fills all the way up. And that way you can ensure that it fills with water completely. Yeah, so this is another thing that I want you to draw on the side. If you let water in from above, it will just take the shortest path possible. It will not fill up the condenser fully. So when you let water in from below, it will settle until finally it exits from above. So this is correct and this is wrong. Okay, so we let water in from below, out from above, not the other way around. Just ask yourself what happens when you pour water in the wrong way. You know it won't work. It won't fill with water completely. Okay? Finally, on the opposite side, we have something dripping out. This is the distillate. And they will ask you what is missing in here. If we do not put an ice bath here, well, the substance will, if it is very volatile, it will just vaporize again. So as a precaution, yeah, not a must, but it's best that you do this, we will use an ice bath. So the ice bath is to prevent volatile compound from vaporizing. So to prevent volatile compounds such as aldehyde from evaporating. Okay. Yeah, so I would suggest that you memorize the whole setup, okay, where things go, okay, where do they belong. Yeah, and finally, we put the mixture of alcohol and oxidizing agent here. So ROH plus oxidizing agent in here. So anything not clear about the setup first? Why things belong where they are? Make sure the thermometer, there are a few key points to know. How water enters, how water leaves, and where you position the thermometer. They all matter. Okay? That's what heat with distillation means. Now we look at heat under reflux. We will just detach the cell. You know these are two quick fit setup. If you have done distillation before, you know these can be freely assembled and disassembled on the fly. So we can just detach the condenser and put it vertically like that. And just like on the left, you want water to go in from below. So here, in, out. For the same reason. You want the water to just circulate like that. And then finally, it leaves. Okay? Yeah, this is the condenser. The full name is Liebig condenser. Okay? Named after the scientist who invented it. Okay? Maybe here, traumatic childhood. Okay? To grab this name. Okay? Anyway, you have the round bottom glass as usual, and then finally you have the alcohol and the oxidizing agent. So when do we use heat under reflux, and when do we use heat with distillation? It depends on what you want to get. Okay, yeah, you can put down the heat source from below. Then you have the Bunsen burner. Yeah, so this is the heat from below. In both cases, you don't heat it directly. Yeah, you heat it through a water bath indirectly. Okay. When do we do reflux? Let's go back. You can see that when you want to do reflux, it's usually when you want the oxidation to be as complete as possible. Okay. What do we mean by complete and incomplete oxidation? You see alcohol in here. If you want alcohol to go all the way to the terminal, like you know when you're taking MTR, you want to push it furthest to the right. Whenever you want the reaction to go to completion, you see that we use reflux. Reflux ensures that the oxidation reaction goes as complete as possible. But sometimes, let's say you don't want to go to the terminal, okay? You want to like a light somewhere in the middle station. Yeah, if you want to do that, use distillation. So distillation will prevent the oxidation from going fully. Okay, that's how I understand it. Reflux would ensure that the oxidation goes as completely as possible. And distillation will stop the reaction in the middle. Yeah, you can maybe put this down. Reflux is used, okay, to make the oxidation reaction go to completion. Okay. So an easy way to remember this is there's only one instance where you use distillation. Is it this one? All other reactions you use reflux. Okay? But then some of you may be wondering, so how does reflux work that allows an oxidation reaction to go to completion? What is so special about the reflux setup that it allows the reaction to go to completion? Let me show you this on the next page. Any question about stuff on this page first? No? No? Okay, so this is the how, this is on how reflux allows oxidation to go to completion. So we have this quick review here. We have primary alcohol, they can stop temporarily at aldehyde before they will oxidize again into carboxylic acid. Both of these steps require oxidizing agents. Okay, let's see what happens inside the setup in here. So I will just draw it really quickly here. I want to show you what is seen inside. So draw 3 round water flask here. So at first, you have in your flask the primary alcohol. The primary alcohol would come into contact with some oxidizing agent to become aldehyde. And let me check if you have done revision on the stuff we discussed some time ago. Which of these substances has a higher boiling point? Primary alcohol or aldehyde? Let me show you the structure and you tell me from the structure. This is what an alcohol looks like. Generally, of course. This is what an aldehyde looks like. Which of these is capable of hydrogen bond? Which of this cannot form hydrogen bond? This one can or cannot? Can. This one? Cannot. Yes. So therefore, the 2 intermolecular forces that you learned is van der Waals and hydrogen bond. Let's put a tick and a cross in these boxes here. For alcohol, it's capable of both van der Waals and hydrogen bond. But aldehyde is capable of only van der Waals. There's no hydrogen bond because it lacks OH single bond. Do you see any OH single bond in here? No. But we see OH single bond in here. So therefore, the boiling point of alcohol is actually greater than that of aldehyde. Remember? Okay, so alcohol has higher boiling point than aldehyde. Which means as soon as the alcohol becomes oxidized to aldehyde, which thing would boil off first? Aldehyde. So this has a lower boiling point. This has a higher boiling point. So as soon as the higher boiling point alcohol becomes oxidized to aldehyde, it will want to leave. So you see, it's trying to escape now. But something stops it, the condenser. This is why we put the condenser vertically, okay? So look at where the aldehyde will go. The aldehyde, you see, it will try to escape through this chute, okay? So through this chute, so you have the condenser in here, you see. In the condenser, of course, there is a lot of water. So the water, for those of you doing physics, you know it's a very good coolant, okay? Even biology, okay? You know, like it has a very high specific capacity, okay? So it can absorb the heat from the aldehyde. So as the aldehyde makes its escape, okay, through the condenser, it wouldn't be able to escape fully. That's because the water carries away the heat from the aldehyde. So when it's cooled down, it falls back down. Okay, so you see it plummets back into the reaction mixture. And this means it will come into contact with the oxidizing agent again. So you see aldehyde will face the oxidizing agent again. And in this case, it will finally be terminally oxidized to, what is the terminal product? Carboxylic acid. Okay. This is why I said reflux will always allow the reaction to go to completion, because it doesn't let anyone escape. It doesn't let anything escape. When the aldehyde wants to escape, it will be stopped by the condenser. If the condenser is put vertically, the water from the condenser would cool whatever thing is trying to escape down. And as they cool down, they lose the kinetic energy and they fall back down. They fall back down into the oxidizing agent. So let's put down the steps in here. So the lower boiling point aldehyde will try to escape, but it will just try. It cannot really escape. Okay, so it will try to escape. And then what? The aldehyde is cooled by the water in the condenser, so it loses kinetic energy. Okay, and it's condensed back into liquid. You know, when things is back in the liquid state, it will not rise anymore. Only vapor can rise. So it will try to escape as vapor. But then the RCHO vapor will be cooled by the condenser and condensed back to a liquid. So as a liquid, it will fall back down. Okay, so as a liquid, RCHO returns to the reaction mass vessel. Okay, so to the reaction vessel, where it reacts with the oxidizing agent once again. So finally, the reaction will only go to completion, and you have carboxylic acid inside your reaction mixture at the end. Do you all get it?
Can you zoom?
Yeah. So you can put down the sequence of events like this. So yeah, the aldehyde will transfer. The most important thing is this one. Yeah, when they ask you the connection to microscopic world to intermolecular force. Okay, so can you put down when the Wiles force plus hydrogen bond together, they are equal to overall intermolecular force. So overall intermolecular force. Because both of these forces, when the Wiles and hydrogen bond, they count towards the overall total intermolecular force, you can see that alcohol will have stronger IMF in total because it has both van der Waals and H bond. And aldehyde will have weaker intermolecular bonds in general. Okay, this is why it will have a lower boiling point. Okay, make sure you know why this has a lower boiling point and why it is the aldehyde that's trying to escape. Why doesn't the alcohol want to escape? Because this is the lower boiling point one. The lower boiling point one will escape instead of the high boiling point. So can you put down the conclusion below? The conclusion is that the primary alcohol will be completely oxidized into carboxylic acid when it is refluxed. Okay, yeah, when it is, yeah, you can also use reflux as a verb. Okay, yeah, so refluxed. Okay, right, reflux. Any question about how reflux would help push the reaction to completion? Okay, now let's go back to the more hands-on activity here. How do we predict the formula of the aldehyde? We already saw that primary alcohol will become aldehyde, and aldehyde will become carboxylic acid, right? How do we predict the formula? Okay, so yeah, finish copying this first. And then we'll, so here we'll look at this part. The determination of the formula of the oxidation products. This is the hardest part, okay? I believe, okay, so oxidation products. We have this pathway, right? Remember, primary alcohol. I'm sorry I bring this up over and over because it's that important. We need to know how to convert a primary alcohol into an aldehyde and finally to carboxylic acid. So can you all copy this? We have AlCH2OH. It's just a general formula because I want to show you what actually happens during the oxidation. The first stage will involve the removal of two important hydrogens. These two hydrogens, okay, so can you help me circle them? One hydrogen comes from the OH group. The other hydrogen comes from the carbon bonded to an OH group. So theoretically, you may as well remove these two hydrogens, not only these two. Yeah, but one of the H must come from the OH group. The other H comes from the C bonded to the OH. So you can put down, this is the first definition of oxidation. So we have oxidation as the loss of hydrogen. Two strategic hydrogen. One from the OH group, the hydroxyl group. One from the C bonded to the OH group. So bonded to OH. Which is why I said you can also remove these two H's. You see, this H fits the second requirement. It is an H bonded to a carbon connected to an OH, right? So we remove them. So when you cover these, look at what happens when you cover. When you cover these, you will have RCOH left, right? Yes? And we have to manually add a bond in here. Yeah, because if we just have RCOH here, they are just free bonds. And remember, carbon always wants 4 bonds in organic chemistry, right? Yeah. So this is why we manually add a bond in here. Okay, yeah. Then manually add a bond between C and O and turn it into a double bond. That's the first step. That's how we convert a primary alcohol into aldehyde. Sorry, I will have follow-up question, but make sure you get the general formula first. What about the second definition of oxidation? Anyone remember other definition of oxidation? How-
Oxidation.
Is it loss or gain of electron?
Gain.
Oxidation is loss of electron. Remember oil rig, right? Oil rig. OIL means oxidation is loss of electron. We can use another more obvious definition of oxidation. Oxidation can also mean gain of oxygen, right? Yeah. So where do we add the oxygen? So it is as if now we are taking a pair of scissors. We cut this bond off in the middle and we stuff an O in between. This is what you get on the very right hand side. You'll have R, C double bond O, O. You see we're basically tearing the C and H apart, squeezing an extra oxygen in. That's what we mean here. Okay, can you put down the instruction here? An extra O is inserted between the C and H. That's it. So to see how well you understand the general formula here, this is extremely important. Can you put 2 stars in here? If you don't remember this, you cannot predict the formula of the oxidation product. These are the oxidation products, RCHO and RCOR prime, and these is carried out by oxidizing agent. So remember, this is distillation on the left, and this is heat under reflux on the right. So let me give you this example. Let's start with something easier first. CCOH. So this is ethanol. Maybe I'll just write the formula, sorry. So CH3CH2OH. Can you predict the product of oxidation when I distill ethanol compared to when I reflux ethanol? Okay, copy this question first. So deduce the products of oxidation of ethanol, okay, when I distill it and when I reflux it, okay, so this plus distill, this plus reflux. So this is part A and part B. Now I'll show you what to do for the first example. We'll do it together, and then starting with the second example, I need you to work on it yourself. So the first thing is to convert CH3CH2OH into a form that we understand. You have to convert it into this form. So how do you turn it into RCOH, H, and H? So let's draw out the bonds. Okay, so turn it into this form. Let's draw all the bonds. Which of these carbon is the carbon connected to the OH? Is it this one or is it the second one? The second one, yeah, you might maybe using some highlighter will help. Okay, so you can highlight the OH group in here. Yeah, so we have C, OH, H, and H. What do we put on the left of this yellow hydrogen, yellow carbon? What is the remaining group? CH3. Do you notice that the R group does not react in the reaction? Which is why it's important that you isolate it out first. Okay, so the R group really doesn't concern you. Okay, it is there all along. Nothing will happen to it. And this is exactly that. The CH3 will not experience any change. Okay, so we need to do that. So we need to convert it into this form. And then now what? When we do distillation, what would this thing be turned into? We will remove 2 hydrogen, right? So let's remove 2 hydrogen. Let me finish this group. This is the end of this. Yeah. Let me remove these 2 hydrogen. When you remove this hydrogen, you will have RCOH. Remember to turn it into a double bond. Yeah, this is the product you will get when you do distillation. And the second one, remember what will happen if I reflux it further to convert that into carboxylic acid? What do I need to do?
Add a hydrogen.
Add an extra oxygen between the C and H, right? Yeah, so we will have this product, CH3COOH. Do you see how we do this prediction? Okay, yeah, we'll pick up from here next time. Okay, do you all understand? Okay, if you have a question, come to me now. Okay, student.
What's up?